Hey guys, can you hear me?
Yep. Yes, Professor.
All right, sorry about that. I think
Yeah.
when the dialog box popped up to say this meeting is being recorded, I think I hit do not accept accidentally, which kicked me out of the meeting. So that's a fun way to start a lecture, right? All right. Okay, so let's get started, everyone. Thank you for joining. We've got 37 participants so far, so I'm sure some more will stream in. Today's an exciting lecture. So today we're going to get into real production level deep learning stuff. You're going to learn a stack today that I use on a daily basis and that many deep learning practitioners do. So really we're kind of in the big leagues now. We're using really cutting edge stuff. So I hope you're excited. So let me go ahead and just do a quick screen share just to kind of talk about the schedule, and then I'll hand it over to Arvind and Rohan for any announcements from their side. But here's our good old schedule. And we are in the deep learning module. I hope you've enjoyed it so far. Actually, just for fun, I'm just curious. This is something I would ask if we were in person, probably. What did you guys think of PyTorch last time, right? I'm sure some folks had used PyTorch before. For those of you who are new to PyTorch, any impressions, any thoughts from last lecture? What did you guys think so far, what we covered in this deep learning module? So Sean said he liked the reading before class. Yeah. So Sean, that piece of reading, I think you're talking about this article, I think, Sean. What is torch.inin really? So if that is what you're talking about, this is a really great article. And if you look actually at who wrote this, right? So who wrote this? Jeremy Howard. So Jeremy Howard is the author of fastai, which is the library we'll learn today. And this article is great. I think he really introduces PyTorch really nicely. I definitely stole some ideas from his article when I made my lecture. So yeah, if you're interested in learning more about this, this reading is really good. Great. Okay, yeah, reduction of lines of code is really nice. So great. Okay, excellent. So here we've made it to November 5th, and today we're going to get into some real sophisticated deep learning. We're going to really train some models today, so I'm excited to get into it here. I do have one quick announcement. We are going to push back this project deadline. This was coming up pretty quickly, and I know there's some groups who are still kind of scrambling to figure out some pieces. So if you're having any doubts, please schedule additional meetings with us. Email us. We're here to help. The semester will be over soon, so please do be working on your projects. We're going to push this back by, I believe, a week. Arvind and Rohan will make an announcement about this today, and we'll push this back on the schedule so you have a little bit more time for the next phase of your projects. Arvind and Rohan, any announcements other than the change in that due date?
Yes, Professor. I see few students have not submitted their codes on Canvas. So I would encourage them to do it today, as today is the last day of submitting those codes on Canvas.
Thank you, Rohan. Yeah, so remember that your official grading for the programming challenge is not through AutoLab. This is it's a university requirement. I wish that could be your official grade, but your official grade is through Canvas. So yes, please submit your submissions through Canvas. Thank you, Rohan. Any other announcements, guys?
Nothing from my side, Professor.
Okay. Okay, and just one other small little announcement. I believe we will have one of the top submissions. I believe we've been talking to some of the top contenders in the programming challenge. So I believe hopefully at the beginning of next class, we'll have one of our top submitters share some of their code. So I'm really excited about that. I've been looking at some of the top solutions, and yeah, some really cool stuff. Some solutions are a little bit more, like I would say, kind of simple tweaks, simple adjustments, and some are just very extensive, right? So you see a broad range of solutions. So we're working on getting it lined up so one of the top submitters can share their code. We're shooting for Tuesday next week. So I hope you're looking forward to that. I think it's a great idea. We just got to get it lined up. So that should come next week. Any questions from students before we hop into the lecture? Anything on your mind? Okay. All right. Well, welcome to fastai. This is going to be a great lecture, I think. Okay. Well, the topic is great. Hopefully the lecture will be good too. It's definitely a cool topic. So here we are in the repo. So this is the deep learning repository, or the repository for the deep learning module in this course. And I just want to point out a couple things. So here's all our material. Today we're going to be using a service called Colab. And actually, if you guys wouldn't mind, Rohan or Arvind, would you guys prepare just a quick poll and just put it up when it's ready, and just ask students, please, if they've used Google Colab before. It's just a simple yes, no.
Yes, Professor, I'll do that.
Thank you so much. All right, cool. So we're going to be using Google Colab. It's a really nice tool. I'll explain it in a little bit more detail in a second, but it sets up your whole compute environment for you, which is really, really nice. So I just want to talk a little bit about your computing environment. So up until now in the class, you pretty much could get away with just using like your laptop, like that was probably fine. This is the first time where that's going to become really painful, and I would not I would not advise it unless you have some really cool gaming laptop with like a nice GPU on it that runs Linux. Okay, great. So Rohan, yeah, if you could go ahead and open that poll, that'd be great. So Rohan's going to launch a quick poll just to see if you've used, so the question here is, have you used Google Colab? So if you could answer that poll real quick, I'm just curious how many students have used Google Colab. I'll keep chatting while you guys are answering. Maybe Rohan just close the poll in maybe 30 seconds or something like that. And the question is, have you used Google Colab before? Okay, so a little bit about computing environments. So like I said, you're really going to need a GPU to do some of the stuff we're going to cover in this series and to do your programming challenge. And I think the poll's done. Yep. Okay. So yeah, 70% of you have used it. Okay. Great. Awesome. Cool. 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 Okay. Colab is a nice service. It doesn't do everything you'd want, but it's very nice and it's free. There's a nice free tier. So that's great. Thank you for setting up that poll, Rohan. Okay, so as far as using a GPU, right, there's a few options, and I'm going to lay out 3 options for you. The first option really is Google Colab. What Google Colab is, and maybe it's probably easiest just to show you. So I'm going to click this button that says Open in Colab, and it's actually going to open up one of the notebooks from this repository. So if I go to Notebooks, this is opening up the second notebook, which is Image Classification with fastai. I've opened that with Google Colab. And actually, with Google Colab, it's really cool. So if I go to, I think it's colab.research.google.com, I can actually open up any notebook that's on GitHub. I just have to put the URL here. So if you want to use other notebooks and use Google Colab instead of your own Jupyter notebook, you can do that. So you can point this at any URL that has a notebook there, and it will load it. It's really, really, really impressive. But this is Google Colab. And it probably looks pretty familiar for the 30% of you who haven't used it. It should look very similar to a Jupyter notebook. There's a few things that are different about it. But the really cool thing, so as I'm sure you've learned, to use the different packages and things in this course, you've had to install requirements and install probably Anaconda Python, things like that. Google Colab does all that for you, and generally you don't have to even tell it what to do. It just figures it out. So when we go import fastai, it's going to figure out that it needs to install fastai in some cases. So it really handles the environment for you. And on top of that, the other really cool thing is I can go to runtime up here, and if I go to change runtime type, I can switch to a machine that has a GPU. You can also use TPUs, a tensor processing unit. This is Google's really, really accelerated hardware. In practice, I haven't found these to be great. Not that it's not good hardware, it's just very specific, so you have to have a very optimized code in my experience. So you're welcome to try this. In theory, it is significantly faster than a GPU, but in this course, we'll be using GPUs. So I'm going to go ahead and turn that on for this notebook. So that's really your first option as far as GPU usage, is to just use Google Colab. It's really easy. Your second option, and I wouldn't recommend this to the average student, but if you are an enthusiast or you are doing any kind of work in this field, or you're doing research and have some budget for this, the thing that I prefer really is to work on my own Linux machine. So I've got next to my desk right now, I've got a desktop computer running Linux that has a GPU on it. This costs some money. You have to buy the hardware, so I wouldn't recommend it if you're just getting into the space. But I think if you're going to be spending a lot of time on deep learning, having this can be really nice. And then finally, you can also rent a virtual machine in the cloud. I do this sometimes for work. And for automated training, we use this all the time. So you can rent a virtual machine with a GPU for about $1 an hour, which is not bad. $1 an hour is not too terrible. So Sai is asking a really great question. So Sai says, is Linux required or is Windows fine? So Sai, in my experience, it's going to be much harder to use Windows for this kind of work. You can maybe use Mac OS because it's Unix-based, but Linux just makes everything a lot easier in my experience. I haven't tried on Windows in a while. I switched to Linux a decade ago or something. But from what I've heard, it's still very challenging on Windows, and a lot of these packages are not supported on Windows. So I would highly recommend Linux if you're thinking about setting up your own GPU compute environment. especially for deep learning. So Supreet says VirtualBox is free, pretty flexible on configuration as long as the host has a GPU. That's cool. I haven't tried VirtualBox. Great, yeah, awesome. There's a bunch of options out there. There's also some kind of middle tier options that do some of the configuration for you. So yeah, these are broadly your options, and there are other options out there. But for this course, you will need some compute acceleration. And for most students, I recommend Google Colab. I think that's going to be all you'll need for for this module. Now, for your project, you may want to use a VM. It's going to offer some stuff that you can't do in Colab, but you may be able to just use Colab on your project. We'll see. It depends on what you're doing, how much deep learning, things like that. But Colab is a very nice option to have. Okay. So that's all I'll say about computing environments. So I have opened this notebook in Google Colab, and I've changed the runtime type. I've changed it to GPU so we can go nice and fast. And now we'll just get into lecture. So let's hop into it. What is FastAI? What are we doing? Okay. Excuse me. So what is FastAI? So FastAI is a high-level machine learning API and library that sits on top of PyTorch. It's written by these people along with a couple other folks. This is Jeremy Howard. He's kind of probably the lead developer on FastAI is what I would say. Before he worked at FastAI or founded FastAI, he was I believe a co-founder of Kaggle. So he had a bunch of experience in machine learning. His lectures are really interesting. He thinks about programming on like a different level than I do. He's super smart. Like he has a whole course on this. He also has a book. It's one of the recommended readings for this course. You can read it all for free online. Here's the book, Deep Learning for Coders in FastAI and PyTorch. It just came out. I haven't read the whole. There's whole parts I haven't read yet. I'm looking forward to reading it when I have some time. But they have a book and a course, and it's really top-notch stuff. If you're looking to go deeper, I highly recommend the course and the book. And again, for the purposes of this course, no need to buy the book. You can read it all online. If you want to buy the book, feel free, but you're not obligated by any means. Okay, so FastAI, like I said, is a software package and a course. And really, it's like a high-level PyTorch wrapper. Some folks in the course may have used Keras. So Keras is kind of like PyTorch, but Keras is a TensorFlow wrapper. Generally, I think Keras can also work with Caffe, I think, and maybe some other backends. But FastAI is going to be a little bit different than Keras. I would call FastAI very opinionated. So what Jeremy Howard has tried to do, which makes FastAI kind of unique, is he's tried to build in a lot of machine learning and deep learning best practices into the library. This can make it a little bit different than other libraries you may have used, so you'll see that. But the whole point is that it's supposed to be very easy and fast to get very, very good results very quickly. So you'll notice that as we look through FastAI. I'll skip over some further details until later about FastAI, but I think if you're looking for kind of an analysis of which frameworks you should be looking at, in this course we're going to be using PyTorch and FastAI. On your projects, if you are doing deep learning, which not all groups are, but if you are, I would recommend FastAI in general, but there's some times where it might make more sense to use TensorFlow or Keras. Especially if you found a good open source repo that's close to what you want to do that uses TensorFlow, then that could be a good option. And there's some other options with TensorFlow. You're kind of plugged more into the Google ecosystem around TensorFlow. So there's some advantages. But as far as kind of experimenting and getting started, I really like FastAI and PyTorch, and I promise you, spending time in those frameworks, it's rarely a waste of time. Okay, so that's enough about FastAI. Let's do something. So you remember way back, I think this was like lecture 1, right? In lecture 1, I introduced you to this really fun, we called it the original problem. And remember this group at MIT back in the 60s? They tried to develop computer vision algorithms to recognize balls, bricks, and cylinders. And you guys are all already familiar with this. You have taken part, I think most students in the class took part in the original problem programming challenge. So you have played with this kind of data before. So as part of this course, I, with the help of some of my TAs the first year, and in the second year actually, we created a data set we're calling the BBC 1000 data set. So it includes some of the data you've already seen of bricks, balls, and cylinders, but we've actually expanded it. So we have 1,000 total images. So we've gone a little further, and we've taken 1,000 images and labeled them all with segmentation masks, which you'll see soon, of balls, bricks and cylinders across all different kinds of backgrounds. So this is the data set we'll be using in the course, or in this module. And I'm going to go ahead and download it. So I'm going to use, so I'm going to run this anyway. Cool. Excuse me. So this is my download script. It's just going to download a zip file from a server that I have this data set on. You'll download the data from the same server. Hopefully it won't take too long. And this is downloading not to my local computer, right? This is downloading to a server that I'm running this on in the Google Cloud. Okay, so we're downloading this data set. And while we're doing that, we can kind of get going with the next steps. And what I like to do sometimes for fun is to kind of code this from scratch in fastai. So we might try that. Let's see if I can insert some blank cells. So Control M B. Oh yeah, there we go. I'm going to insert a few blank cells, and we'll start playing with. We'll see what we can do. All right. So this data set is 99% downloaded. It's almost there. Okay. And I'm about to import fastai, and then we'll see what we can do with fastai with this data set. And generally, the idea here is we're gonna take this brick ball cylinder data set, and if you remember, back in Programming Challenge 1, you guys wrote code to tell apart bricks, balls, and cylinders. And Arvind and Rohan, do you guys remember the top score this year? I want to say like 78%, something like that.
Oh, yes, Professor. Let me check. I can get
No
back.
problem, thank you. So you guys, I know a number of you worked very hard on that challenge, and some of the top submissions were maybe high 70s, low 80s. And let's see what we can do with deep learning. That's what we're going to do basically, right? Same problem, let's apply deep learning and see what we can do. So it seems like my download has decided to stop at 99%. That's kind of like the election results, right? We're waiting for that last few percentage points. So hopefully this finishes. Thanks. Yeah, I got a couple laughs for that corny joke. All right. That's all. 73. Okay, great. So you guys worked your butts off on Programming Challenge 1, and yeah, 73%. Okay, great. So let's see we'll see how deep learning compares to what you guys were able to do in that first programming challenge using analytical computer vision. And yeah, Abhijit sees where this is going. If I if I said, oh, deep learning's worse, that wouldn't be a very good lecture, right? So that's funny. All right, I wish this download would finish. Goodness, I can't run this until I get, maybe I'll start a second notebook. You know what I am gonna do? I'm going to go ahead and open the next, we're gonna cover 3 notebooks today if it goes well. I'm gonna go ahead and kick off the second notebook, so at least I'll have that download done. So we won't be stuck in this same pickle pretty soon. But I gotta change my runtime, change runtime type to GPU. Cool. All right, I have to run this again. Oops, let's see, like that. Okay, so I started this download at least. All right, I'm afraid I'm gonna have to restart this. So I'm gonna restart the runtime. Kind of a bummer, but that's okay. We can deal with it, and hopefully the second time it will go a little better. Whenever you run code live, something will go wrong. So if you've been invited to give a talk or do something where you're coding live, just know something will go wrong when people are watching you. The code knows, and it will. If there is a bug that can happen, it will. So just be ready for that. That's been my experience anyway. All right, so we're 40%. Oh yeah, switching off video. Yeah, although the video latency, because this is not downloading to my machine, right? This is just downloading to a server. So let me know if I have any audio issues, and I'll switch off the video. Oh, we made it. Okay, great, cool. All right, so I have downloaded the data set. I'm going to import the library fastai.vision. So this is the vision component of fastai, and I'll make this a little bigger. It looks like it might be a little small. Okay, cool. So this is the path to my data, and I'm using what's called the Python pathlib library, which gives us some nice options and nice ways to see around what's going on. So when I run path.ls, this tells me what's in this folder. Now Colab makes this nice and easy because I can actually just click here and it will show me, what's the file structure, where we are. And it looks like I actually had already had downloaded this, which is cool. But we have some data, and you could certainly poke around it here. I'm going to poke around it using ls, but you could look at it using a file browser as well as part of Colab. So here's what I've given you. So I've given you, so BBC stands for brick ball cylinder. I've given you a folder called masks, a CSV file called classification labels, a folder called images, and a JSON file called bboxes. So we'll kind of poke at all this. This shouldn't actually be here. This is just my stupid file on my Mac system that got uploaded, so ignore that. So let's have a look at images real quick. So if I go like this, I'm going to do path / images. So this is the path to my images. And I'm going to do an ls on this, I think is what I'll try first. Yeah, so in this image folder, there are a bunch of images. You can kind of see them all here, and they all have unique numbers. So we need to figure out how to load these up. And kind of what I'm doing here is I'm just walking you through how a normal process works in fastai, just to back up a little bit. So I want to train a model, hopefully to classify bricks, balls, and cylinders. And we'll do more stuff with that data soon. But first, I just want to see if I can classify, and I want to see how fastai compares to what we did in the very first module. So the first thing I have to do to train a model is to load this data somehow, right? So how does data loading work in fastai? So instead of just showing you the code, I'm going to kind of walk you through the thought process. And the first thing I do usually is just kind of poke at the data, what's in here. Here's some images. That's great. Very cool. What I really think I want to look at, though, to kind of make some progress, is let's look at this classification labels thing. So let's do that. So I'm going to use a library called pandas, which we haven't used in this course yet. I'm going to use, let's see, I think it's from CSV, I think is the method I want. For some reason, my autocomplete is not working too well. I may have to cheat. We'll see. Did I not import pandas? No, let's see. Oh, read CSV. Thank you so much. I always get those backwards. So yeah, read CSV. Great. All right. So read CSV. All right, cool. So I'm going to read this CSV file here. So the way I can do that, I'm going to copy that. I got to say Command C. Okay, like this. All right. So I'm going to do path / There we go. So this should, yeah, I think this should actually read it. Let's see. No such directory. All right. So the joy of coding live is you get to run into these kinds of issues. I think this should work. Let's see here. So yeah, that's a path, and I believe that, ooh, I have this, oh yeah, so yeah, I've got the same thing twice. Yep, that's embarrassing. So what I really need is just need that. There we go, cool, all right. So this is the CSV file that I provided you, and I'm going to do this, okay, cool. So I'm gonna call this labels. I'm gonna call this CSV file labels. I'll say labels equals, okay. And in pandas, ooh, of course that doesn't work. All right, why would that work? All right, like that. All right, there we go. I'm gonna do labels.head. This will give us the very top of the data frame. So cool. This is our CSV file. It has a list of file names that matches up with those file names we saw. It has the label names, and I also gave you a label index, which might be useful here and there. But this is our data, right? Okay, cool. Alrighty, so hopefully that makes sense. Now, how do we get this into fastai, right? And just a disclaimer here, we're going to be using fastai 1, but fastai 2, which is kind of the rewrite of fastai 1, it has actually just come out like late last or earlier this year. However, I tried to switch over these lecture notes to fastai 2, but we actually lost some performance, so we are going to stick with fastai 1. But just know that fastai 2 is out there, and you might want to look into it if you're using it in your project. For this module, though, we're going to use fastai 1, and then as soon as I figure out why our performance isn't as good in fastai 2, I'm going to try to switch over. But for now, we're going to be using fastai 1. Okay, so we are going to use this thing called an image data bunch, and this has a slightly different name in fastai 2, so just be aware of that. But in fastai 1, we're going to use this thing called an image data bunch. And it's really like a data loader. It's this really nice class that does lots of nice things for us. It lets us load our images quickly to train a deep learning model. So I'm going to use a constructor method called from df. So this lets us build an image data bunch data loader from a data frame is what it lets us do. And you can see in the doc string here, it's asking for a bunch of stuff. We're going to hand it a few of these things. It wants a data frame, it wants a path, it wants a label delimiter, which we may or may not do. Let me start kind of piecing these things together to show you what they do, and then we'll kind of check back in with this doc string. So I'm going to call the result of this data. We're going to make this data loader. So the first thing this thing wanted was a path, I believe. So let me see if I can get that there. Cool. So it wants a path. That's a path to your images, and it wants a data frame. So let's do that first. So for path equals. Okay. So the path to our images. So we are in right. So I believe we need to hand this, and bear with me here. I'm kind of doing this with you the manual way just to show you. This code is actually below, and I might reference it if I run into issues, but let's see how far we can get. Oops. One problem, one annoying thing is that the keyboard shortcuts are slightly different in Google Colab, so that can be a little annoying sometimes. Okay, so I'm going to give it a path, and the path to our images, it should be, yeah, I did copy the whole cell, yep, accidentally. So the path to our images are located here, data BBC train images. So I believe our path needs to be here. I think it needs to be this whole thing. So we'll try this. And yeah, I guess there's no just copy text here, right? Yeah, that's why that's confusing. So if I take this and I'll just hit Command C on Mac to copy that. There we go. That's what I wanted. All right. And I'm going to give it a data frame, which is our data frame of labels. So I'm going to pass in this whole labels thing. And now, folder is like the folder where your images are located, but I've already kind of taken care of that with path, so I don't think I need it, but we'll see. We'll come back to it if we get an error. Label delimiter, so there's, in fastai, you can do what's called multi-class classification. So if an image contained a ball and a brick, for example, we'd want to be able to detect both of those. But here, every image only has one brick, one ball, or one cylinder for the most part, so we are not going to pass in this label delimiter thing. Valid PCT, let me ask the class real quick. What do you think this does? Valid PCT, any guesses what this fastai data loader argument does? Yeah, great, Abhijit, good. So this is the percent of data to use as a validation set. And this is what I mean by fastai kind of encoding best practices. It's actually very hard in fastai not to have a test or validation set. They almost force you to do it, right? So we'll use the default here. We'll use valid PCT, and I could just leave it blank and it would use the default, but I'll just type it out so we can see it. So I'm going to do valid PCT equals 0.2. So this will automatically split off 20% of our data to use as validation or as a test set as we train. Seed, I'll skip that from now. That lets you have the same, and it lets you choose the same set every time, basically. FN column, this is really important. This is the file name column. So notice that our file name column is called file name. So for FN column, it's just called FN call. Yes, I'm going to type in file name like this, file name. Okay, I'm going to scroll down a little bit so you guys can see a little better. All right, great. And we also need, so I have the file name column. I should have to pass in a label column. Yeah, so I'm telling fastai what is the name of the column in our table that contains the label. And here it's just called label. So I'm gonna say label underscore call equals label. Okay. And maybe for fun, sometimes in Python people do stuff like this and it can make things a little bit easier. So I'm gonna try this. So here's our 5 arguments. And I think I'm going to pass in some more stuff in a second, but let me just try this. Let's see if fastai gets mad at me. Okay, it hasn't, right? So fastai is not mad at me, but let's see if it really has what I want. Oh yeah, this is great. Yep, cool. So I just printed out data. And data's, we'll get into this more later, but basically it's saying, hey, for your training set, you have 754 items. Here's some of the labels, ball, brick, ball. Here's the size of your images. And here's your validation set. You have 188 images. Here's the size of those images. Here's some labels. So our data loader is coming along pretty nicely. That's awesome. Okay. So I thought I was going to mess that up the first time. All right. I know after using this library for a while, and you can find it in the documentation, that I can pass in a few more things into this data loader. And I'm going to go ahead and do that now. So fastai. Yeah, Akshay, good question. So Akshay asked, where's the cylinder label, right? So Akshay, it's a great question you asked. So I'll make that a little more clear in a second. This printout only shows the first 5 examples, So the first 5 examples just happen to not have a cylinder, but there will be cylinders, and we'll prove it to ourselves in a minute by visualizing some of the data. So yeah, really good question. This is just showing the first 5 examples. Great question. Okay. So let's do this. I want to actually train on smaller images. If I train on smaller images, it's going to go faster at the beginning. There's a bunch of reasons that are nice to do it. We can make them bigger later. But I'm going to pass in, I think I can just pass in size, I believe. I'm going to try downscaling our images all the way down to 128 by 128. And wow, that's a fun warning. Wow, goodness. I believe that is related to a version difference between Torch and FastAI. Hopefully that warning doesn't persist a lot. There it is again. Ugh. All right. I may suppress that warning in a minute, but for now, we'll ignore it for now. At least we won't let it slow us down. I think this is a versioning thing. We're using FastAI 1, and it has to have a certain version of Torch, and I'm guessing, I don't think it's a problem, but I just think it's they're just trying to warn us that something is possibly incompatible. Okay, so notice what our image size is now. So by me putting in that size thing of 128, I've had FastAI, the data loader, downsize our images. And this is going to help us train faster. We can make them bigger later, but training on smaller images first is a good idea. It helps you go faster and just kind of learn more quickly at the beginning. Okay, I'm going to type in one more thing. BS, I think, is the last thing I'll type. Actually, no, 2 more things. I'm going to say BS equals 32. You don't have to pass this in, but I'm going to do it real quick. It won't be obvious right away what I'm doing, so I'll take some guesses. And we'll talk about this a lot more next week. We haven't talked about this in a lot of detail. Does anyone know what BS stands for? What does BS stand for? Yeah, batch size. Thank you, Hernan. So when we train these models, so far, you've been doing what's called deterministic, you've been doing what's called batch gradient descent, basically, or deterministic gradient descent, where you take your whole data set and you put it in the neural network at one time, right? In practice, you're not going to have enough memory on your computer to load the entire neural network, or the entire data set in at once. So typically, we feed our data to our neural network one batch at a time, or one mini batch at a time. And we'll get into batch versus mini batch next week. It's really just semantics, but here I'm saying, please feed my neural network 32 examples at a time. And you can increase this or decrease this. The main reason you would decrease it is if you ran out of RAM on your graphics card and you got an error. But there are other reasons why you might prefer a smaller or larger batch size. Smaller batch sizes actually lead to less overfitting sometimes. We'll talk about that next week. And there's one very last thing I want to do, and we really have not discussed this idea at all yet, but it's the idea of data augmentation. Data augmentation. And again, this will be a topic for next week, but I'll just introduce it now, and it's so easy to do in FastAI that we're just going to do it, and then we'll learn more about it next week. But the idea of data augmentation is I'm going to synthetically flip and transform and change my images just a little bit. And by doing that, I can make my model learn more effectively, because it's like you simulate having a bigger training set. So there's a great method in FastAI called get transforms. And this does a bunch of synthetic modifications to our data. You'll actually see it when we look at some visualizations in a minute. But it changes the lighting, it rotates the images a little bit, it flips them. And you can change how much it does all of these things by changing these values. But I'm just going to use the defaults. So to do that, I believe I can just pass in this method. So I'm going to do tfms equals that. And it's going to give me an error. Great. Let's see here. What do we got? Is that not what it's called? I believe we handed in here. So I made my first mistake of the day in FastAI, which is okay. I was kind of waiting for this to happen. So I thought we handed it in here, but yeah, it doesn't want to take a TFMS argument. Interesting. Okay. All right. I'm going to have to cheat for 1 second. So I'm going to go back and look at what I wrote the first time. Let's see. What did I do? DS transforms. Okay. Yeah. So this argument is called DS transforms. And I forgot that I normalized this last time. Okay. Cool. All right. So I'm going to pass in my transforms like I just mentioned. And the keyword argument for that, which I forgot, is ds underscore transforms. Transforms equals, and I'm going to do get transforms. So don't worry about the syntax too much. Not important to memorize or anything. You'll get used to it if you end up using FastAI more. And then finally, I did this normalized thing before, which is where you divide your data by certain normalization parameters. Oops, I cannot talk and type at the same time. All right, bear with me. DSTFMS. There we go. Cool. All right. So all those warnings again. I might try to suppress those in a minute if they get really, really annoying. Where do I have that code in here? No, I don't have it. I'll have to grab it somewhere else. Okay. So that is our data loader. And if I run this, it'll give me a bunch of warnings again, but it will print out, hey, here's your data set. And now let's really get into it. So we've made a data loader. And the first thing I'm going to do is I'm going to show some data using this show batch command. And this will actually show us, after giving us some more warnings, it will show us a visualization of some of our data. So that should load in a second here. Hopefully that pops up. It's funny, I wasn't getting these warnings yesterday when I ran this notebook. I'm not sure what changed, something with the version. Okay, so here is a visualization of some of our data. Here it is. And it's showing you your images and your labels, which is nice. So we've got a brick, and to answer your question, Akshay, here is a cylinder, so it is there, right? Which is great. Here's a ball. Some of these are hard. I hid this ball behind that leaf right there. That's pretty tough. You know, imagine trying to solve some of these problems as you did in the first programming challenge, you know, without a technique like deep learning. So there's our data. That's great. So now we want to learn from our data, or we want to train a model. So we're going to use this fastai method called CNN Learner. And this is going to set up a neural network for us. Yeah, so Abhijit's right. A human might not be able to find those things, right? Yeah, definitely. Some of these are questionable if a human could do it. Absolutely. Okay, so we're going to make this thing called a CNN learner. So this is like an object in FastAI that contains your neural network. And a CNN learner takes some data. You have to hand it a data object, which we already have. And it takes what's called a base architecture. So in FastAI, there's a bunch of different models you can choose from. Here's a list of some of the models. And we're going to be using, I think, what's called ResNet 34 in this case. So does anyone know what the 34 is for? What does this 34 mean in ResNet 34? Yeah, it has 34 layers. So imagine that, right? So, you know, so far we've used like a 1-layer, 2-layer neural network. This one has 34 of them, right? That's why it's called deep learning, because it's many layers deep. So yeah, this is a 34-layer neural network. Notice there was also like a ResNet 18, there was a ResNet 50, so you're welcome to try other ones. ResNet 34 is usually a pretty good starting point. So I'm going to pass in models.resnet34 for our next argument here. And I think I'm going to give this a keyword name. I'd like to at least. Let's see. I guess I'll do this. What is that keyword argument? If I do a question mark. Okay. So yeah, base architecture. Cool. So don't worry about some of these other arguments. If you get deeper into FastAI, you can worry about some of this other stuff. Just know that generally FastAI is going to try to take a best guess for you about what a good configuration is. So I might not, well, yeah, I can use the keyword. So yeah, this is our base architecture. And then for the last thing we'll pass in is what's called metrics. So metrics is how do we want to measure our performance? And we're going to measure our performance using accuracy. So I'm going to type in, so accuracy is actually a method, I believe it's a method, that was imported by FastAI automatically when we imported FastAI at the beginning. Yeah, fastai.metrics.accuracy. So we're going to pass that in as what we'd like to measure. Now this is really cool. Let's see, so it gives me a bunch of printouts. Oh, actually, I can eliminate some of those by doing this. Do learn equals. Yeah. Okay, there we go. Cool. All right. So I've made this learner thing. That only flashed up for a second, but then it went away. You might have seen a download bar. Let me actually do this. You'll see one now if I change the architecture. So yeah, that was super fast. Wow. Does anyone know why did, when I set up my learner, right? Does anyone know when I set up this deep learning model, why did my notebook download 100 megabytes of data, right? Any guesses when I ran this, right? Why did it, yeah, the weights, right? Now, why wouldn't I just use random weights? So far in this class, I've just said, hey, just initialize them. Yeah, so Jagadish, great. So we're gonna cover this next week, guys. I'm kind of giving you a bunch of the tools now, and then we'll talk about some of the whys next week. So yeah, so it turns out that if you take one of these deep learning models and you do what's called transfer learning, where you take a model that's already been trained on a big data set. This model was trained on the ImageNet data set, which we'll talk about next week. It turns out if you do that, you perform a lot better. So this is a pre-trained model that we're going to call, it's called fine-tune. on our data set. So this is a really good way to go. It can really get you good performance quickly. Okay, so we have this learner thing. Now, the next thing we're going to have to do with fastai, and this is just a nice example of kind of the nice things that are built into the library. We're going to run a method called learn.lrfind. Learn.lrfind. Any idea what this does? If you think you know, throw it in the chat window. What do you think learn.lrfind does? And I'm going to run it, and it's going to give me a bunch of warnings while we're talking. Man, none of these warnings were here yesterday. All right, thank you. Yeah, Siddharth, thank you so much. That was the block of code that I was wondering if I had already. We might just add that right now. Yeah, this is going to help us find the best learning rate. So let me go ahead and bring in this great little snippet of code from Siddharth. Thank you so much. That's one thing you can't do in person, right? It'd be hard for Siddharth to send me some code in an in-person lecture. So that's pretty cool. So Monica asked a great question, and she said, does everyone do that? Use a pre-trained model, even like in the corporate world? Yeah, yes we do. Yes we do. I get that question a lot. Yeah, yes, it's kind of become standard best practices. So yeah, let's talk about learning rate. Yeah, so Abhijit's asking if it's adaptive, and I'm wondering if this LR find is still running. Let's see, I might stop it for a second, and I will answer your adaptive learning rate question in 1 second. It's a great question. Interrupt execution, cool. Hopefully that works. Let's see. Seems like it's still spinning. Okay. Yeah, it's taking a little while. Hopefully we have the right runtime, right? Let's check. We are on GPU. Great. All right, so I'm going to try to run this again, and while I do that, we'll talk about adaptive learning rates. So if you did this programming challenge and took it seriously and worked on it for a while, you probably experimented with a learning rate. I'd be surprised if you didn't. The learning rate is probably the most important hyperparameter, right? Picking the right one can have a huge impact on your performance. And as far as I know today, no one has really figured out a great way to automate this. There's some things you can do, but it's difficult. It's a difficult parameter to choose. So fastai has a nice way of doing this. And this is not fully automated, but it's helpful. This is going to help us find a good learning rate. Now, in fastai, they do use this concept of what's called a cyclical learning rate, where the learning rate does change, but it's not adaptive. It's not changing based on performance or anything. So that's a good thing to know. I might have to just kind of scratch this whole thing and start from the top, maybe skipping the dataset download. So let's see here. Here's what I'm going to do. So I'm going to take this warnings, this great snippet here, and we're going to, hopefully that helps us avoid our warnings. There's one more line. There's like a simple filter ignore or something that you need sometimes, but we'll see. So I'm going to restart my runtime. So Colab is being a little bit finicky, but we're going to try again here. So there we go, there's that. Okay, cool. Let's see if we've actually suppressed our warnings. Fingers crossed. Okay, so I'm loading up those labels. Man, Google Colab is just fighting us today, right? I said so many nice things about it, and now it's now it's just hanging. All right, well, hopefully it agrees with us shortly. Yeah, I'm just trying to visualize my data frame. Is there anything else similar to Colab, Monica asks? Not that I know of, that'd be nice, but no, Google has really invested in this, which is nice. It's like Google Docs for notebooks, right, which is a great idea. It's a great idea when it works. And I don't think it's my internet. So Arvin is gonna run in parallel, sure. Kaggle notebooks, yeah, sure, right, good point. Okay, right, so we're struggling here. JavaScript output, Google account, login access has expired or third code. Oh my goodness, all right. This is the danger of live code. We've had pretty good luck live coding, except for when my model, except for when a week ago when my power went out. We've had pretty good luck in this class. Okay, I think we're doing a little better. Seems a little bit less fussy. Oh yeah, Azure Notebooks, yep. I haven't used Azure Notebooks extensively, but yes. All right. Try running the cells with love. All right, I'm sending my love to the cells. It's an issue with the output actually, which is kind of interesting. All right, here's what we're gonna do. we are going to close this. AWS has a service called SageMaker. I might lose some of my work, but that's fine. And that still isn't finished either. Goodness. All right. So here's what we'll do. We're going to go back here. We're going to reopen this. And this should be kind of a fresh start, I believe. Yep, cool. All right. So thus far, here's what we've done, guys. We've downloaded our data set. We've imported fastai. Let's try this again here. Oops, runtime we want to be change runtime type, because it's time for us to train a model, right? We gotta train one of these, right? So here we go. Let's see. Okay. The universe does not want you to see how easy it can be to do deep learning. Okay, come on. It's saying something with my credentials. Yeah, I will import warnings if it's a good point. If those pop up again, I definitely will. Okay, come on. Try one more thing on the side. I'm going to create a new window real quick. You guys won't be able to see this window, but I'm going to try a backup thing real quick, where I'm going to try a different Google account, actually, because it was complaining about my account authentication. So I'm going to try my UNCC. I'm going to see if I have any more luck. And if that works, I will switch my screen share to that screen. So just bear with me for 1 minute, and we'll see if Colab will be a little bit less fussy. So let's see if I can run this. Okay, runtime type, change runtime type, GPU. Okay, all right, bear with me, guys. Okay, so I'm in another page now, working on, and is this one, oh, this one finally ran, I think. Maybe we're in business. Okay, maybe we're okay. Oh yeah, okay, let's keep going here. All right, I've got a backup one too, just in case. All right, cool. So here's that image data bunch thing. And it's not warning me now, which I don't know why. Maybe it's because I didn't change the size. Oh yeah, no, I did change the size. All right, not sure. Okay, so now it's gonna show me, we're gonna visualize our batch. Here's our batch, so we already saw that. Now we're gonna create this CNN learner thing. We're gonna use ResNet34. Oh yeah, one more little thing that I didn't tell you about. I'm gonna call this learn.freeze thing. So this is another concept in deep learning, which we'll come to more. So this model has many, many layers, and it turns out when you're initially training, it can be helpful to only train the last few layers. Those last few layers in fastai are called the head of the network. So by calling learn.freeze, I believe by default it is frozen, but I just called this again just to make sure. Learn.freeze, and I'm going to go ahead and start our LR find while I'm talking. Learn.freeze freezes the first like 30 layers, something like that. And only learns the last few, which can help us at the beginning learn more quickly and be a little bit more stable. So I froze our network, and now I'm running this LR find thing, and it actually is running. And I know it's on GPU because on CPU, this would be way slower. So here's the thing, though. Let me just talk about it for a second. I haven't told you how LR find works, right? Any guesses out there? You kind of see that it's doing some computation. Any guesses what LR find does? So it involves cross-validation, but it's a little bit different. You know, if you wanted to find a good learning rate, right? So more details, good guess. Give me some more details though, right? If you wanted to find a good learning rate, what could you do? What experiment could you run to figure out if you had a good learning rate or a bad learning rate? I see some good guesses. No one's gotten it yet. What would be some experiments you could run? So sure, gradient descent, but like, you know, how do you know if you found a good learning rate? What could you measure? Yeah, we can measure loss, right? And I haven't told you the loss function. Actually, fastai has chosen a loss function for us, which we'll talk about in a minute. That's using what's called a cross entropy loss. But what you can actually do is you can try different loss functions. Excuse me. You can try different learning rates, and for each learning rate, you can take one step or several steps downhill. You can do gradient descent, and you can see which one most reduces the cost function. So that's the idea here. I'm going to run this thing called learn.recorder.plot. So here it is. So as we change our learning rate and take a step downhill and do some gradient descent, this is how much our loss changes, right, as a function of our learning rate. So this can help us choose an ideal learning rate. So based on this plot, does anyone have a guess? What would be a good learning rate, right? What would be a good learning rate? So Hernan says 1e minus 3, okay? So Videhi and Abhijit say 1 times 10 to the minus 2, and Ravina says 1 times 10 to the minus 1. Yep, okay, cool. So right, So this big learning rate is going to really drop down your loss, which is great. In practice, you want to back off this a little bit. So I would personally do 1 times 10 to the minus 2 here. I'd back off this by about an order of magnitude. You can also look at the slope. The more the slope is, the more this should decrease your loss as you train. So I would recommend 1 times 10 to the minus 2 here. I wouldn't do anything up here. Otherwise, our loss is going to go up. Remember, that's because our step is too big and we like bounce out of our minimum. And over here, this is kind of too slow, right? So 1e minus 2 should be a good learning rate. It's not way here at the top, so it shouldn't be unstable, but it should learn a lot. So that's what we're going to try. Oh, and actually, that's funny. I was just preaching to you about doing 1e minus 2. I ended up doing 5e minus 3 in my experiment, so a little bit more back here. But either one of those should give good performance. Okay, so I'm about to run this method called fit one cycle. Fit one cycle. And this does a few different things for us. I'm pulling out all the deep learning stops to show you what it can do, and then we'll kind of break it down in following lectures. So fit one cycle, what it does is it trains for one, it's called a cycle, and it actually varies the learning rate. So the learning rate will actually, it'll follow this cosine curve. It's been shown through a couple of papers that if you change the learning rate as you train, it starts at 5e minus 3, but then it changes, and then it returns back to, I think, 5e minus 3. If you do that, you get better performance. So we're about to do that. We're going to train this thing. Does anyone know what the 4 is, right? What is this 4? So I'm saying fit one cycle, and the first argument I'm handing is 4. Any guess what this 4 will do? Any guess? I didn't give it a name, a keyword argument name. What will this 4 do? Any ideas? Batch is a good guess. So Hernan got it right. This is epochs. So what is an epoch? Hernan or anyone else, what the heck is an epoch? I don't think we've mentioned that in this class. There's a bunch of new words today because we're really getting deep into deep learning. So it's close to iteration psi, but it's not quite the same. So yeah, Monica, you said it pretty well. So we're going to run through the entire training set 4 times. So one epoch is one pass through the entire training set. So one epoch is one pass through the data set. Here we're going to take 4. You can kind of choose an experiment. 4 is usually kind of a nice starting point. There's one more thing we're doing here. We're doing this kind of crazy slice thing. This does what's called a differential learning rate. I wouldn't worry about this too much. I won't quiz you on this, but it's just another trick, another kind of best practice you can use to get better performance. And what a differential learning rate does, it won't matter too much because our model's frozen right now, but a differential learning rate uses a different learning rate at the early layers than it does at the later layers. It uses a smaller learning rate at the beginning and a bigger at the end of the network, and that can improve performance as well. Austin says, in this case, and Austin, let me start this model training, and then I'll answer your question. We can watch the model train as I answer your question. So good question. Let's hop into it. So I'm going to run this, and it's going to start training. So it's going to count the epochs. We're going to look at the training loss, the validation loss, and the accuracy. And while that's training, I'll talk to Austin. So Austin says, it's a great question. He says, in this case, is it a time through the batch you send it, or still the whole set? I think I understand your question. Maybe you can rephrase just a little bit. Yeah, just rephrase a little bit for me to make sure for the epochs. So you break down your overall training set into batches. So here you can actually look. So see how there are 11, this 11 here? There's 11 mini batches in our overall training set. So it breaks the training set into 11 sets of, I think, 64 examples, whatever we put in earlier. And it goes through those one at a time. So that's the idea of an epoch. Cool, yeah, good question. So here it's showing our training loss, our validation set loss, and it's showing us our accuracy, right? And what do you already notice about accuracy, right? So let's see, where is it going to land on after 4 epochs? Let's see, yeah. Okay, so we hit 94.6. How do you guys feel about that accuracy? Impressed, not impressed? What are your thoughts? Is that good for this data set? Could be better. Not sure yet. Okay, well, remember that this was the data set that you guys worked your butts off on the first programming challenge, and the very best, we had a competition, and the very best score was like, what was it, 70? So yeah, sure, accuracy can be bad metric, no problem. We'll get into this in more detail, but like, I just want to emphasize that like 95% on something like this was not possible like 10 years ago, maybe even 5 years ago. So like, as far as compared to like analytical approaches, like for these kinds of problems, this is crazy. But you're right, we should be suspicious of accuracy. Maybe I've made you guys too suspicious by trying to trick you sometimes. There's not a trick on this, really is good performance. So let's keep going, let's see if we can make it better, and then we'll look into it in more detail. Here, accuracy is actually not a bad metric because our classes are relatively balanced, but yeah, you should be suspicious of accuracy. I agree. So I'm going to unfreeze this thing, which is going to let us train the whole network, and we're going to see if we can get better performance. I'm going to do LR find again because we might have a different learning rate that would work well now that our network is unfrozen, and we're going to be training the whole thing. So let's let this run for a minute, and it should give us we'll get another plot, and we'll pick a learning rate here. So let's see. Let's see where we end up. It's funny. You guys were nervous that this wasn't good performance. It is good. It is good. This is and I think we're going to get really high performance. We'll see. We'll see what we get, what we're able to achieve here. So this should end shortly, and then we should be able to pick a learning rate. And I might skip ahead a smidge here. From the last time we ran the notebook, this was the plot we got. And notice that things kind of shifted, right? So now it looks like, let me ask the class. Yeah, so Austin says, did we change the epochs to 10? Well, no, this is not training. Good question. This is just finding the learning rate. So it tries 10 different learning rates, basically. Yeah, good question. So looking at this plot, guys, what looks like a pretty good learning rate, right? Looking at this plot, what learning rate do you think would be reasonable for our next phase of training now that we've unfrozen the network? Yeah, I see some 1e minus 4. 1e minus 3 is maybe a little high, right, because it's way over here. 1e minus 4, maybe even a little more back. I think I'm going to hit 5 times 10 to the minus 5th. And actually we have our new plot ready. Oh, that's kind of different. But yeah, 1e minus 4 is probably about right. I'm going to do a little bit back for that. I'm going to do 5e minus 5, so like right here. So let's train. We're going to go ahead and train for 8 epochs. Let's see how we do here. So I'm training this guy again. And we're learning from 800 examples, something like that. And the training is pretty fast, right? So it wasn't always this fast. A lot of improvements have been made. But we can knock out an epoch. You're seeing it take only about 10 seconds to take a whole pass through our training set. One other thing I want to point out real quick is that it's showing you your training loss and your validation loss. Excuse me. So what you can do is as it's training, you can watch and you can say, okay, am I overfitting, right? How would you know? What would happen to these numbers if you are overfitting? What would you see in a chart like this that would indicate that you are overfitting? Yeah, so what number would be bigger than what number? So Abhijit, they would diverge for sure. What number would be bigger than what other number? So if valid loss is bigger than train loss, yeah. And sometimes it's a little bit bigger, but and that's maybe okay. But if it really gets big, then you're in trouble. So another question for you guys: do you think this accuracy is being measured on the validation set or the training set? What is your guess? How do you think FastAI works? So I see some both ways, yeah. So this is actually on the validation set, which is good. It means that this is a pretty reliable number. So even if you are overfitting, this will still give you your performance on your validation set, which is a nice thing to have. And you can see we're hitting 97, 98%, which for a problem this hard is like really mind-blowing. Like I said, this was really just not possible 5 or 10 years ago to do this kind of image classification, especially this quickly. Okay, so we're almost done training. I think I actually got 100% on this the other day, but I think we're going to land around 98, something like that. It depends on your test train split. So we hit around 98% accuracy, and we could train more and we might do better. We're not really overfitting yet. Ravina, this is not a trap, I promise. That's so funny. This is the least trappy lecture, I promise. I've been trying to trap you all, and not to be mean, just to make sure you're thinking critically. But no, this is, I promise. There's no trap at the end. This is all good stuff. That's funny. All right. So here is our confusion matrix. Here we go. So have a look at this, right? So we got 75% 75 of these ball examples right, 73 and 36. We only missed 1, 2, 3, 4 examples total, which is pretty awesome. FastAI includes a confusion matrix plotter by default, which is great. So you can just run this, get your confusion matrix. And there's another method that I really like. It's called plot top losses. So this is super cool. What this does is it ranks all of this is the validation set. You can do it for the training set as well, but it takes your validation set and it says, okay, which examples did I do the worst on? Did I miss the most, right? So it shows you the prediction, the actual label, the loss, and the probability. We'll get into the probability later, but right now, so in this case, the network is saying brick. The network thinks it's a brick, but it's actually a ball. There's the ball. It got it wrong, right? So these are the 6 times, and actually we only missed 4. So actually you should only see Like this one, yeah, this one's actually right. It's still a high loss example. The network almost got it wrong. It's only 73% confident, basically. But it was a challenging example, but it still got it right. So, but you can see that it missed this one. That's pretty interesting. It thought there was a ball here, and maybe something looks like a ball. Maybe that looks like a ball, maybe. But there's a cylinder here. It thought this was a brick, which is kind of interesting. Maybe there's some square edges here or something that look kind of brickish. Here, the ball is hiding behind the plant, kind of, so that's tough. And here it thought it was a cylinder, maybe because there's like a cylinder-shaped thing here and a cylinder-shaped thing here, so who knows, right? But it only missed 4 examples on our test set, and no tricks. This is real performance. So I think that's pretty incredible, right? So just within less than an hour of messing with fastai, we've achieved a classifier that performed 98% accurate on this brick ball cylinder classification problem. So I hope that makes sense. We'll get into the details of how this works, but what I really want to point out is that, especially in regards to your course projects, if you're looking at using deep learning, fastai can get you going really, really quickly. You can get good results like this very, very fast. So that's classification. We've only got about 15 minutes left, so I want to show you some more stuff. But this is kind of the most basic thing that you can do with fastai is you can train a classifier, and really you can get just some amazing performance really, really quickly. Okay, so that's classification. I want to get into another kind of problem that we can do, a problem called bounding box detection, or sometimes just called detection. And let me see here. I bet I already have a data set. So this is the second notebook for today. And I need to change my runtime type. And this is where we're going to get into kind of like modifying fastai a little bit and not just using the stock fastai. So let's get into that here. And I think I already have my data set. So let's find out here. Let's see. And I'm importing all this stuff. I didn't realize until recently that actually, if you just run this cell, it actually runs this and this for you. So you don't have to import all this stuff, but not a big deal. Okay, so let's see here. So Diego says, how long does it take to create labels for a big set without labels? Yeah, so classification, Diego, is pretty fast. I mean, mostly you can just drag your images into folders. If you have 3 or 4 or 10 classes, just put your images in folders. There's a method in fastai called image data bunch from folder, and that will let you, if you have a set of folders, like if we had our data separated into a brick folder, a ball folder, and a cylinder folder, we could load data that way. That's pretty easy to label. Now for this data set, you'll see shortly that we have segmentation masks and bounding boxes for in our labels. That takes longer, right? But Diego, this is an 1,000 example data set. It probably took me 3 hours to take all the pictures, maybe another hour to process them and to be the same size and stuff. But the labeling, I don't know, hour, it's not bad. Like if you're just classifying stuff, you can label really, really quickly. Now we also, like I said, drew bounding boxes. That probably took 6 hours, something like that, maybe 5. But it's not as bad as you think. Labeling is not too bad. I also always feel very productive when I label. I don't know why, but I just feel like I'm getting a lot done. Let's see here. Okay, I did not download this yet, so let's download this. Okay. All right. This is what I tried to download, if you remember at the beginning of lecture, but I had to restart this notebook because Colab decided to pretend like I didn't have credentials for a while. All right, so let me introduce the problem a little bit here. Let's see if I have a nice visual to show you. Yeah, here we go. So this is going a step further, and it's saying, okay, can I use fastai to not just classify an image, but to figure out where in the image the brick is, right? And fastai does not actually do this out of the box. If you are working on a problem for your course project where you have to do bounding box detection, I actually don't recommend using fastai. I'm mostly showing this to you today just to show you what you can do with fastai and give you a feel for it. But if you're doing bounding box detection, I recommend looking at a library like YOLO. So we'll cover YOLO a little bit later, but here's like a nice open source implementation of this model called YOLO that does bounding box detection for you. And this is just going to be a little easier to work with, and you're going to get better performance for this specific bounding box case. Bounding boxes are the one area where fastai does not really have a good solution that you can just use right out of the box. But I still want to show you how to do it in fastai because it's good practice. And if you're doing something non-standard for your course project and you need to modify fastai, this is a great way to learn about how to do that. Okay, and we'll learn about bounding box detection. Okay, so here's our data again. And if you remember, I also gave you this big JSON. I gave you this JSON file. And this JSON file, if I load it using json.load, I see that I get this dictionary back. And this dictionary includes a few different fields. It has an images field, an annotations field, type, and categories. And if I kind of drill down into the annotations, so I look at annotation number 12, for example, and I look at this B-box field, and I kind of just jumped ahead a little bit here. If I was just exploring this myself, I might start by doing this and just kind of see what that prints out. So yeah, I get a bunch of these annotation things. I see it's a list, so like maybe what's the length of my annotations just to see. Scrolling is a little weird. Okay, so yeah, there's 1,185 of them. There must be one per image, I think. So if I look at the 12th one, I could look at the 12th annotation for a second and see what's the structure of my data. I see that, okay, there's a bunch of stuff in here. There's this thing called segmentation. These are all the points that make what's called a segmentation mask. We'll get to that later. But the thing we're going to be using now is what's called the bounding box. So we need to figure out how to set up our fastai data loader to get this data into a format that we can use to train our model, right? That's the idea. And this is our bounding box. That's the thing that we really need. So I just wanted to show you where that was in the JSON file. And you will be working with this data set for your programming challenge. So just be aware of that, I think, as you're watching. Okay, so fastai has a method called get annotations. And these JSONs are in a standard format called the COCO format. And get annotations, what it does is it imports two things, a list of images and a list of bounding boxes. Let me show you that real quick. So when I run this, I get two lists that are the same length as our data set. Here's the first 5 entries in the images list. Those are just the names of our files. And here's the first label bounding box. And it includes the coordinates. These 4 numbers are the coordinates of the corners of our bounding box. And this is the class. So this get annotations method from fastai, this imports these things pretty quickly for us so we can start working with them. And what I'll go ahead and do is just show you a little visualizer. So I'm loading in one of these images. I'm loading in image number 2. I could load in image number 20, for example. It'd be a different image. There it is. I'm using this open image method from fastai. I'm using this image bounding box create method to create a bounding box, and then I'm visualizing it. So that's the idea here. So there it is. Hopefully that makes sense. And I'm going a little quickly here. Again, the semantics are not super important. You'll have a closer look at them when you work on your programming challenge. But now what I'm doing is I'm making a data loader. I'm making it in a little bit different way. I'm using a different fastai syntax, but I'm doing the same thing. So I'm loading in what's called an object item list from a folder. Then I'm splitting my data, and I'm using 20% for validation. And then I'm labeling my data. I won't have time to cover this today, but I have this little function called getY function. And this actually, it just tells the data loader what the name of or how to get the label, basically. And then I'm applying some transformations. I'm not rotating. It turns out if you rotate this, the bounding box changes in kind of a weird way, and I don't want to do that right now, so I'm not rotating for my augmentation, but I'm doing some other augmentations. And then all I'm really doing then is just picking a batch size. Yep, cool. So I'm going to make a little data set with a batch size of 64, and I'm going to downsize my images to 256 by 256, and I'm going to have a look at them. So I'll run this again, and we'll get a look at our data set here. And the thing I really want to get into is how do we modify our neural network to be able to predict bounding boxes? And this is actually really cool, and we're going to run out of time in a minute, but let's see what we can get in here. So here's our data set. This one's a little bit off. That label must be a little bit off. We might have labeled it a little bit differently or something. But most of these look pretty good. That one's a little bit off as well, maybe. But there's our data set. And now what I really want to get into, like I said, is our model. So I just want to kind of show you how flexible these learners are. That's what I really, really want to get into. And this is going to be some torch code, which should be a little familiar from last lecture. So here's what I want to cover. So if you want to make a neural network, right? If you want to make a neural network, detect a bounding box, right? A bounding box around a brick, ball, or cylinder, for example. First of all, does that feel like a classification or a regression problem? First of all, what do you guys think? Classification or regression? Yeah, so this is a classification problem. Great. Oh, sorry, no, regression problem. Sorry. So this is a regression problem. I went with the majority for some reason. That's funny. So this is a regression problem. It's regression because we're trying to find this bounding box, right? So this bounding box, it has, the way you parameterize this generally is you have some numbers that describe the upper left corner and the bottom right corner, right? So it's actually 4 numbers. So there's 4 numbers, and if you can have your neural network predict the value of those 4 numbers, then you have found a bounding box. So it's really like a regression problem. I hope that makes sense. We're trying to predict 4 numbers, the coordinates of this bounding box. That's what we're trying to predict with our neural network. So here's where it's going to get really interesting, I think. So we're going to use this thing called a custom head, which is an idea in FastAI. So we'll get into this in more detail next week. But the idea of a custom head is I can have this big, deep, long neural network, right? And then at the end, I can add just a little bit of extra neural network, and I can kind of tailor that to predict what I want or to do what I want. So this in dot sequential thing, yeah, so Monica asked a good question. She says, those 4 numbers will be in a range like classes. Not quite, Monica. That's a great question. Well, I mean, they are going to be in a range. So the numbers your neural network will predict should be between like 0 and the size of the image. But it's going to predict a continuous number, right? So like the right prediction you want here, if the coordinates of that corner, if this is like down 100 and over 200, you want it to predict the number 100, 200. And it could be a little bit shifted. So in some cases, you might want it to predict, 101, 201, for example. So we want it to predict 4 continuous numbers to find the 2 corners of the bounding box, because each corner needs 2 numbers. I hope that makes sense. It's a good question. Okay, so you hopefully remember that in dot sequential thing. This lets us set up little neural networks. Here are, and this is in PyTorch, and again, FastAI is built in PyTorch, so we can hand in PyTorch things. So in dot sequential lets us set up a neural network. Here we're just setting up part of a neural network, and FastAI glue it together with the whole big neural network. This is just kind of what's called the head, just the end of the neural network. We covered this very briefly last time. Does anyone remember what adaptive concat pull 2D is? Does anyone remember what does this do for us that's kind of nice? Does anyone remember what's nice about this layer? So this lets us address a problem that we see, which is sometimes if you want to change the input size of your image, it could break your neural network. This allows you to have any input size, which is nice. So we're really out of time here. I was hoping to talk through all of this today, but we'll pick up on Tuesday and get into this in more detail. But I think at this point, I've thrown a bunch of deep learning at you, and I'm doing this module in a little bit of a different order. Usually, and this is actually the philosophy FastAI follows. The FastAI teaching philosophy is give you everything first and then break it down, basically. And normally, I don't actually like that philosophy. It's not the style. There's nothing wrong with it, but it's not the style that I like usually. I like to build progressively. But in this module, I've decided to follow the FastAI method, and I'm showing you everything. So if it feels overwhelming, that's okay. I'm throwing a bunch of stuff at you, right? We're going to spend the next 2 weeks breaking this back down. But I want you to have the very best cutting edge tools for your project, right? So if you're doing deep learning in your project, FastAI is a great option. So after today's lecture, you've seen the kind of the cutting edge of this stuff. And we'll continue on Tuesday, but please have another look at the lecture notes. Do look at the programming challenge. And we'll pick up and break this down more next time. But if it feels like I'm throwing a bunch of stuff at you, I am. So please hang in there. FastAI is not too bad, but it's a bunch of new stuff. But I promise all the work that you've put in, all the thinking that you've put in into learning about neural networks and machine learning, it's going to be really helpful. You've got a strong foundation from this class so far, and we're just going to build on that with deep learning. So we're out of time. Monica's asked a great question, which let's have a look at real quick. But if you need to leave that's the end of the lecture. So thank you today for coming. We'll see you guys on Tuesday. you should be in full swing on your projects. So projects should be going. Make sure you're working hard on those. The deadlines are coming. So good luck on your projects. And that will end lecture for today. I'm going to go ahead and we'll look at Monica's question real quick. But feel free to leave if you need to head out. Okay. So Monica says, but those 4 numbers will still be in a range. Oh, no, my understanding is that the difference between general machine learning and deep learning is epochs. Deep learning goes through the same data so many times. Yeah, so Monica, that's a great question. As far as the difference between general machine learning and deep learning, it's not about epochs. It's a great question. So in your last programming challenge, you might have done multiple passes through the data. I hope you did. You can get better performance that way. The only difference between deep learning and just neural networks in general is just the number of layers. So I know that sounds like it's just nothing, but deep neural networks have many layers, and the model we're training today has 34 layers. And traditional neural networks didn't have that many layers because no one knew how to train them, right? And they didn't have the hardware. So deep learning just means more layers. That's all it means. So it's the same exact math we did the calculus on. It's back propagation. This is doing back propagation. Everything's the same. Only difference, the only difference on face value is the number of layers. Now in practice, there's going to be like a bunch of tricks, right? So I've shown you some tricks today. There's going to be more tricks, but it's going to be more just like things that work well in practice. But in theory, the only thing that's different is the depth. That's really it. That's really all that it is. All right, cool. All right, so yeah, Sai has a great question. You said adding more layers didn't help in the programming challenge. Yeah, so we have I think next week you'll enjoy one of the lectures. We're gonna show why. So there's a bunch of tricks happening in PyTorch. Just adding more layers doesn't always improve performance, and you have to have enough data really for it to work well. So yeah, just adding layers alone does not make magic things happen. This is why, the neural networks that we learned about in the neural network series, those were really around in the 1980s, but no one knew how to really do deep learning because the hardware wasn't there, and there's a bunch of tricks you have to do to get it to really work. So that's what we're learning in this module. What are all the tricks and things you have to do to make deep learning work? And it's getting easier and easier, but it's still a little hard. There's some tricky parts to it. It takes some time to learn. Okay, guys, well, thank you for your time today. We will see you on Tuesday. Get to work on those projects. We'll see you in project meetings. Make sure you schedule those. And have a good weekend and rest of your week. Thanks, guys.